Hi, and welcome to this edition of Live from NOIRLab at Arizona. I'm your host, Rob Sparks, and we have our moderator, as usual, Jamaica Marshall, with us. Our guest today is Tom Matheson, an astronomer at NSF's NOIRLab in Tucson. He's going to talk about the ever changing night sky. Remember, if you have any questions for our guest, please put them in the chat and we will relay them to our guest, Tom. So I'm really looking forward to this, and I think when you hear Tom's bio, you'll find out why. But first, a few words about Kitt Peak National Observatory. Kitt Peak is funded by the National Science Foundation and is a NOIRLab facility. It's located about 55 miles southwest of Tucson on land leased from the Tohono O'odham Nation. It was founded in 1958. We are indebted to the O'odham for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes as well as 2 radio telescopes. Now I'd like to share just a little bit of news, recent news from Kitt Peak here. It's on the Dark Energy Spectroscopic Instrument. Kitt Peak has mapped more galaxies than all previous 3D surveys combined. The Dark Energy Spectroscopic Instrument, tripping over my tongue a little bit, has capped off the first 7 months of the survey by smashing all previous records for three-dimensional galaxy surveys, creating the largest and most detailed map of the universe ever. The DESI survey has already cataloged over 7.5 million galaxies and is adding at a rate of more than 1 million per month. In November 2021 alone, DESI cataloged redshifts from 2.5 million galaxies in just 1 month. By the end of its run in 2026, DESI is expected to have over 35 million galaxies in its catalog, enabling an enormous and so far unsurpassed variety of cosmology and astrophysics research. The primary task of this survey is to collect spectra of millions of galaxies across more than a third of the entire sky. By breaking down light from each galaxy into its spectrum of colors, DESI can determine how much light has been redshifted, stretched toward out the red end of the spectrum by the expansion of the universe during billions of years it traveled before reaching Earth. It is those redshifts that let DESI see the depth of the sky. The more redshifted the galaxy spectrum is, in general, the farther away it is. With a 3D map of the cosmos in hand, physicists can chart clusters and superclusters of galaxies. These structures carry echoes of their initial formation, when they were just ripples in the infant cosmos. By teasing out those echoes, physicists can use DESI's data to determine the expansion history of the universe. The U.S. Department of Energy's Lawrence Berkeley National Lab leads DESI, which is installed at the Kitt Peak National Observatory on the Nicholas U. Mayo 4-meter telescope. So that's a great program, and I'm looking forward to seeing more of that. We had um, a guest a few months ago, actually Parker Fidelius, last summer, or summer before that even, summer 2020, talk about DESI. So we'll put a link to those in the show notes. And now on to our guest, Tom Matheson. Tom was an undergraduate at Harvard where he worked on ultraviolet observations of the solar corona. And this is an impressive bio here, so buckle up. He did graduate work at the University of California, Berkeley with Alex Filippenko. Tom worked on a variety of topics, but his focus was supernova, with his thesis concentrating on spectroscopy of stripped envelope core collapse supernova. While there, he was lucky enough to work with the 2 teams that discovered dark energy using thermonuclear supernova. Tom shared the 2007 Gruber Prize for Cosmology, the 2012 Aura Science Award, and the 2014 Breakthrough Prize in Fundamental Physics for that work. For Tom's postdoc, he returned to Harvard, working with Robert Kirshner, mainly on supernova, but also gamma ray bursts, something I enjoy a lot. Since 2004, he's been a staff astronomer at NOIRLab. Tom's continued to work on supernova, but have expanded to many other aspects of time domain astronomy. His project to build a software system to project's time domain alerts, Antares, received the 2019 Aura Team Science Award. And so with that impressive background, I'd like to welcome Tom to our podcast. Good afternoon, Tom. You're muted, Tom.
Oh, I am muted. Thanks, Rob. I'll try to live up to the introduction.
Yes, I think you will. So I'll mute myself out and let you take it away here.
All right, you're going to have to stop sharing so I can. Okay. I'd like to thank everybody for tuning in today. And the thing I wanted to talk about is the ever-changing night sky. And I think a lot of us have an impression about the things that change in the night sky. We watch the moon phases change. We watch the stars move across the sky. And as it turns out, astronomers now realize that almost everything that is in the sky is changing, from things near our Earth, the near Earth objects that might run into us, to distant objects in our solar system, to the stars, to distant galaxies. Everything is changing in some way. And we're just trying to understand how those things change and how we can use that information to understand more about these interesting objects. But even though we know that things are changing, I think there's still in the back of most people's minds a belief that there's a constancy to the sky, that things are unchanging. And in fact, it's kind of a metaphor that we see throughout our culture. Shakespeare used the constancy of the sky. So Cassius, when he was trying to convince Caesar that he was still a loyal and true friend, said, "I'm constant as the northern star, who is always fixed and in the same place." But of course, we know that, in fact, the North Star is not always fixed and in the same place, because the Earth spins on its axis and the gravity of the sun and the moon pull on that. The direction in which the Earth's pole points changes over a 26,000 year period. We just happen to have the North Star in the place where we're pointed right now. And in fact, Hipparchus, a Greek astronomer, knew this 1700 years before Shakespeare wrote that play, 100 years before Caesar was born. So even though there is this knowledge of the changing of the sky, there is still this general impression about how fixed and constant it is. And so I hope to share with you some of the things we know about how the sky is changing. So that's what we want to talk about. How this time domain astronomy, and that's what we call the study of astronomical things that change in time. In fact, it encompasses almost all of astronomy, so I could really just call it astronomy rather than time domain astronomy. And I'll talk about how seeing the sky changing has changed the way we viewed the cosmos. In fact, it's been key in changing various aspects of how we understand how the universe works. It's driven forward our view of the world. I'll talk a little bit about how astronomers study these changing objects and how technology is really dramatically changing how we're looking at things right now and how things are changing in the night sky. It's really unbelievably enhanced our ability to harvest all of the things that are changing in the night sky and understand even more about what's going on. And at the end, I'll show you a couple of interesting examples of time domain science. So our ancestors, when they looked up at the night sky, they weren't fools. They learned a lot from watching it. And the night sky was very important to them. It was where they would keep the records of the stories they had and the patterns of the stars. They would use it for navigation. But more important from our perspective is how they learned to keep and study time. Most of the time periods that we use, days, months, years, these are all things that are derived from the rotation of the Earth, the movement of the Earth around the sun. So the time that we experience, the way we live our lives, is really dominated by how the sky changes for us on a regular basis. And so it was studying these movements on a regular basis that really gave our ancestors a way to take hold of time and control it in a way that they couldn't have done without some way to keep track of things on a regular basis. It allowed them to build things, observatories that would line up with certain astronomical events to keep track of where things were in the sky. They could follow things and understand more about their own world by using these tools to record how the night sky changed. But even more powerful than that was that you could use these calendars, this information about how the sky changed, as a predictive tool. You could actually know when things are going to happen based on what the sky told you was going to happen. For example, the ancient Egyptians could tell when the annual flood of the Nile was coming by the time that they could see Sirius for the first time in the morning light, just before the sun rose. And of course, knowing when the flood was coming was critical so that they could maintain their agriculture. They would be prepared for when the flood came, that would fill the fields with fertile soil and allow them to plant the crops that they needed to. They would know when it was coming because of this. And having a calendar, that allowed agriculture to flow across all of the ancient cultures. It gave them a way of understanding when they can plant, when they can harvest, when things are going to happen that are important to them and the world they lived in. And so this led to a fairly rigid cosmology. This is how Aristotle viewed the world, where the Earth was at the center and all of these objects moved around in a very predictable and prescribed way. And nothing was unexpected. Now, things changed on the Earth, and so things like shooting stars and meteors, those were part of the Earth sphere. But everything beyond that was fixed and moved in a way that people understood very clearly. But of course, things up there didn't always move exactly the way you'd expect. This is a time-lapse image showing two different planets, Mars and Saturn, against a background of stars that we would call the fixed stars because they move in a regular way. And you can see that these objects don't move in the same way as the stars do. And in fact, they wander around. And so the Greek word for wanderers is planets. So that's why we call them planets, because they wander around in a way that is unlike how the stars move across the sky. And so this is the first challenge to a world where things move in a simple and orderly fashion. How do you explain the fact that these things are moving in a way that is inconsistent with everything else? And then things became even harder to explain in that kind of vision. When Galileo first used his telescope, and this is the first step of a technological advance really changing things for us, Galileo looked through that telescope and he saw things no one had ever seen before. He saw craters and mountains on the moon. And more important for us here, he saw Jupiter. And when he looked at it, you'll see on the bottom right-hand corner of this, a drawing he made of Jupiter. And there were little points of light around Jupiter. And he noticed that if he looked at it night by night, those points of light moved, and they moved in a predictable way. What he discovered were moons around another planet. And this was a total challenge to the cosmology of the day. How do we understand how something is moving out there in a way that no one could have predicted based on the earlier models? But there was clearly something interesting going on there. There was something different about the universe. So this, along with other aspects of study, like how the planets moved and seeing these changes, helped to drive acceptance of a new vision of cosmology, and that is the Copernican cosmology, where the sun's at the center and things are moving around out there. But there can be moons around other planets, but things still moved in these spheres in ways that were more or less prescribed. You still had to invent a fairly complex system to make the wandering of the planets make sense, but you could do it if you really wanted to make an effort. As it turns out, there are reasons why we understand how to make that work now. But at that point, that was how they would try to explain it. But even with this model, the furthest out sphere, where the stars were, that was still fixed and nothing was supposed to change out there. But at the same time, Galileo, or around the same time Galileo was looking at Jupiter and seeing the moons move around, people were seeing other things change in the sky that were even more dramatic and hard to explain. And the first happened in 1572. On the left, you see Tycho Brahe, who was a Danish astronomer. And in 1572, he saw something that people hadn't, that at least in the records of the European astronomers, they hadn't seen before. Something new appeared in the sky. A star appeared where one hadn't been before. And it wasn't a meteor because it lasted longer than that. And it seemed to move in the same fixed way across the sky like the other stars, implying it was out beyond the spheres of all the planets. It was part of that stellar sphere, someplace where things shouldn't change, and yet it did. And just a few decades later, Kepler also recorded another one of these new stars. And in Latin, the new star was nova. And so that's what we still call these. And an even more energetic one is a supernova. We'll get around to more of that later. But you can see in the center, there's a drawing of the constellation Ophiuchus. And down in his ankle, there's a little bright spot with the letter N next to it. And that's the drawing that Kepler made to show where this new star was. Something new and different that shouldn't be there if things were always the same. And the other interesting fact, of course, is that Kepler actually used the data that Tycho Brahe observed from the planets to derive his laws of planetary motion, further cementing the Copernican theory. But of course, this is all the European perspective. As it turns out, other cultures had noticed things changing in the sky. And in fact, the Chinese and Native Americans recorded a supernova 500 years before any of the European astronomers did. This was a supernova that occurred in the year 1054 that resulted in what we now call the Crab Nebula. On the left, you see the records of the Chinese annals reporting on this. On the right, you see a petroglyph from here in Arizona that indicates that they saw this supernova because of the position relative to the moon is an indication of understanding where it was, and this is consistent with where we think it might have been visible to them from Arizona at that point. So people had recognized this, but still didn't quite understand, how important these changing things were. So all those things had driven how astronomers would think about it. So how do professional astronomers think about how things change. And the way we do this is we track how brightness changes with time. We call this a light curve because it tracks the light. And so if you were to look at this light bulb and come back every hour and see how bright it was, you would record that, you would produce this nice uniform line. It's not very exciting because it's constant. So that's what a constant source would look like. That's what a star would look like if you thought it never changed. But of course, stars do change. And we know this from looking at our own sun. There's a fairly dramatic change there with an outburst. That's not necessarily a common thing happening on the sun, but you can see the whole surface is constantly burbling away. And if you look on the upper right-hand side of this slide, you'll see a light curve of the brightness of the sun. And here it's showing the change in the percentage that we get, a percentage of light that we get from the sun. And so the sun itself varies. But those other stars that you see down below it, those are stars like our sun, but they vary a lot more. It turns out that our sun is actually particularly quiet for stars of its type, which is pretty good because if we lived around one of these other stars, you'd never know what kind of SPF to use because it was changing day by day. At least here we have some idea of constancy, even though the sun is still changing a little bit. So stars are changing, they're varying all the time, but there are other ways they can vary. In this case, here's a star called Algol. And the way this star varies is, in fact, that there are two stars in Algol. There's actually three, but the important thing is the two stars in the middle. These stars go around each other. And every so often, and in fact, in a periodic way, you'll see that it happens every 2.9 days. One of the stars moves in front of the other along our line of sight to that star. And so as it does that, the star in front dims the light from the star behind. And you'll see in that light curve that the star is bright and then drops dramatically as the other star moves in front of it and then comes back up. And then as the brighter star moves in front of the fainter star, there's also a slight dip. So you can see both of the stars eclipsing each other. And so this star actually changes brightness. And this star is visible to the naked eye. You can go out and look at the star and actually watch it dim. And the ancient Egyptians knew that this star varied. In fact, that's why it's called Algol. It means it's the demon star because it was changing. And of course, the stars shouldn't change. So it was really unusual that it did. But the fact that things eclipse each other is a really valuable astronomical tool because we can learn all kinds of interesting things about the stars that do this. We can understand their masses and how far apart they are in much more precise ways if we can see them eclipse each other. And more exciting nowadays, this is how many of the exoplanets that we know about are found, because in the same way a star can move in front of another star, when a planet moves in front of its host star, it very slightly dims the light. And we can actually see that and measure that small difference and see the planet move across in front of the star. And sometimes you can actually see the planets do this on a regular basis. The Kepler satellite has discovered thousands of exoplanets using this exact technique. Another way that stars vary is by an intrinsic pulsation. So there is no other star changing this. This is the star itself. In this case, this is Delta Cephei, the third brightest star in the constellation Cepheus. And it pulses. It swells up and down in a regular cycle, almost like a piston. And as it does so, it gets brighter and fainter. And one of the really interesting things about this is the time it takes to do that tells us how bright the star is. And so that means we can use this pulsating star to tell us how far away things are. We can use it to map out distances within our own galaxy. So this is a really valuable changing object because not only is it interesting in and of itself, but we can use it as a cosmological yardstick. And finally, one of the other amazing things we can do is we can watch stars that explode. And so if you look on this panel on the left-hand side, there's a little arrow pointing to a star. And if you've taken a photograph of the Large Magellanic Cloud, this is a satellite galaxy of our own. If you'd taken that photograph in January of 1987, that's what it would have looked like. But if you came back in February, it would look like the image on the far left, where it's incredibly bright. And that's because that star the arrow is pointing to exploded. And when stars explode, they can get immensely bright. If you look at the light curve, you can see that this one star became 100 million times brighter than our own star. So it's a really dramatic change. And because they're so bright, we can see them far away. And this is why we could use another kind of supernovae where we know how bright they are, to map out distances over an even further greater cosmological distance. And that's how the team that I worked on helped to discover this dark energy. But I think Jamaica's trying to get my attention.
Yes, Tom, thank you. I definitely wanted you to finish first. Thank you so much. Yeah, so we have, I just want to say welcome to everyone in the YouTube chat. Thank you for your comments and questions for today's guest, Tom Matheson. Okay, Tom, first two questions. As you're discussing the ever-changing night sky, we have a question from Liz Flemings of the Memphis Stargazers. And Liz asks, what do you think some of the UFOs actually are that are often visible in the night sky? And I have to say, here on the Big Island, I get this question from some of my friends often. Quite a lot of times it's Venus low in the west when it's the evening sky. But this is definitely a question. So, do you see unidentified objects, and how do you go about making those known or finding out what they are, Tom?
Well, I think a lot of times the things that people see that they think might be UFOs or something like that, it's often planets, because they're bright and they can be low in the sky. And the way the atmosphere distorts the light you can see from them can often make them appear to be brighter and fainter and actually even change color. So I think that explains some of what people see. But as I'll get to later, there are actually many things that we see in the sky that are unexplained. I mean, these are objects that we detect, but we don't necessarily have the information to follow up and explain them. That doesn't make them mysterious. It just means that there are many, many, many stars in the universe. You know, there's 100 billion stars in our galaxy, and there are 100 billion galaxies. There's a lot of things out there that are happening, and we don't necessarily know everything that's happening. And that's one of the fun things about looking at these things that change, is we often find things that we've never seen before. So it's not that they are alien in nature. It's just that these are physical things that have not yet been explained. And so I think that's the interesting thing as far as what astronomers think, is there's definitely things out there that we don't know. But we're going to look for them, and when we find them, we'll try to explain what they are.
That's brilliant, Thomas. Thank you, Tom, for that excellent response. I appreciate that. And we have one more question, and this is from UNFI 6798. And the question was, has anyone checked out the Chinese cosmology calendar? And in the chat, Tom, I just responded there that, I know definitely yesterday was the Lunar New Year. Could you maybe speak on the Lunar New Year and why that changes?
Sure. I mean, the Lunar New Year is tied to the cycle of full and new moons, which actually does not tie up directly with the solar year, which is how most Western calendars are oriented. That's because the amount of time between each full moon is not exactly divisible into the length of the year, and so that means that it changes relative to the time on the Western calendar, and so that's why it moves slightly. The other thing is we do look at the Chinese cosmology. In fact, historical supernovae and other historical events, there are very good records in the Chinese annals, and in fact, a lot of people have spent a lot of effort trying to translate old records and to understand where people were looking, and it's a very valuable resource for people to use. So we do that all the time. And if this were not in the era of COVID and I could do this talk from my office, you would see I have a Chinese star map behind me, behind my desk at work, that I bought at the observatory in Beijing in 1993. So I wish we could be there so I could have that as my background, and then you'd see how important it actually was to us.
Wow, Tom, that's pretty amazing. Wow. I really,
how appropriate.
Yeah, it absolutely is, Rob. Wow. Yes. So you're not there. I was going to say maybe at the end, if you have an image of it, I would actually really love seeing that.
Yeah, I'm not sure I have one easily accessible, but I could find it.
Well, thank you for those very amazing detailed responses. It's actually really good to know that Chinese cosmology is actually something that is used. And I will pop off screen and let Rob continue with his comment. Thank you, Tom. I'll come back when we have more questions.
Okay.
Well, I'm monitoring the Facebook chat, and we have a question from Facebook from Carolita. She says, my 8-year-old son, Eddie, would like to know, what are the chances of a neutron star coming from a supernova? If that's a question from an 8-year-old, that's a pretty sharp 8-year-old. So I'll let you take that one, Tom.
Oh,
well, no, that is an excellent question. And in fact, we believe that supernovae are the origin of almost every neutron star. So exploding stars come in two different types. There's either a massive star that collapses, and this supernova 1987A was one of those, and that's what can produce a neutron star. If this event did form a neutron star, we haven't seen it yet. It's possible in one of these explosions that nothing is left. Sometimes it might form actually a black hole directly instead of a neutron star. But this is the way that neutron stars are formed, is by the collapse of massive stars. And we know that neutron stars have to be part of the process, because it turns out that when this supernova exploded, it actually emitted neutrinos, which is a small subatomic particle that would only be detected as a neutron star was being created in this particular instance. And on Earth, we detected neutrinos that came from this event, and they're consistent with the time when they came. So we know that that's happened. So we have direct evidence that neutron stars could be formed in these core collapse supernovae. And we know that neutron stars exist because we have pretty good evidence from a lot of different sources that they're there. So it seems like, but you do need to have a supernova to make them.
Okay. Thank you, Tom. And Carolita verifies that, yes, Eddie is sharp. So
okay, well, that's good.
Oh, that's fantastic. Thank you, Tom.
All right, thanks. So in addition to all those sort of more or less understandable things, there are other stars that just do weird things that we don't necessarily understand. So this may go to some of that aspect of, do we really know what's going on with everything out there? And there are plenty of cases where we don't really understand it. And so this was a star that Kepler satellite, the one that found all the planets, it was staring at this star that's in the little blue box. And if you look at the light curve, it looks pretty normal if you look at the top couple of panels where it's just cruising along without much change at all. But if you look at the bottom panels, you see it starts to do crazy things. There are dips and wiggles, and some are sharp and some are not. And it's really unclear what's doing all that. And at the time, people even proposed an alien megastructure as what was causing this around the star, of some race trying to collect all of the energy from the star. That's probably not the correct explanation. Nowadays, people think maybe it's a disk of dust around the star that's tilted in some way that produces these odd effects. But still, it's a very unusual and mysterious thing that we don't quite understand exactly how all of this happens. And that's one of the great things about doing this time domain astronomy is you find stuff like this that pops up that is inexplicable, but eventually we'll understand it. It just takes time. So how do we actually create those light curves that I showed you? Well, in the old days, you saw that drawing that I had, that Galileo had made. And that was what people did, is they looked through a telescope and then they either drew a picture or wrote down what they saw. They described what they saw. So this is, for example, William Herschel. This is the telescope he used when he discovered Uranus, is this telescope, but he had to draw it by hand because there was no way to record it. So it was kind of subjective. But you could still look with your eye through a telescope and see things change brightness. People still do that today. The American Association of Variable Star Observers has thousands of people around the world who are constantly looking at stars that are changing and comparing the brightness by using just their eyes. So it is doable that way, but there still is a subjective quality to that. It sort of depends on how well your eyes work, and everyone's eyes are a little different. So it's not perfect. It's not as precise as you might want to do the science. And so we want something that's different than that. And so the first step in turning it into a science was having photographic plates. Because with a photograph, you have an objective record of the sky at the moment that image was taken. So you can save it and anyone can look at it after the fact. There's no doubt about what was actually there. You don't have to rely on someone's memory or their skill with a pen in order to understand what they saw, what the telescope observed. So that was a great advantage for photographic plates. The disadvantage is photographic plates are actually not very sensitive. They only recorded about 1% of the light that fell on them. So that meant that you weren't quite getting everything you could, but still, it was an objective and permanent record. That was a good thing. And you could take a photographic plate and you could go back to the place where you took the photographic plate again, months, days, years later, and you could compare them. And so this device here you see on the right-hand side is called a blink comparator. You'd put two photographic plates in it, and you'd look in the eyepiece, and you'd use a little mirror to flip your vision back between the two of them. And by flipping back and forth, you would see any changes between them. And so the image on the left, you'll see Clyde Tombaugh looking through a blink comparator, doing exactly that. And that's what he did to look at millions of objects to find Pluto, because it moved so it was different as you blinked two different plates. But it took a lot of time and effort to do that. And so it's not easy for one person to really do millions of objects like that. So it's definitely a Herculean effort on his part to find Pluto. So to illustrate what that looks like, I'll show you a couple of slides just to say, I'll blink back and forth. This is what it would look like if I blinked between two images. And you'll notice that something is different between those two. And that's what it would look like if you were blinking between two plates with a blink comparator. You would notice that little bright light appear, a new supernova in that galaxy popping up in a way that you haven't seen before. So I think Jamaica has another question for me.
I do, Tom. First, this is my question. Is this image M51?
It is.
It's one of my favorite galaxies, one of my favorite interacting galaxies to show people and talk about. Okay, that was a great blink comparison. Okay, Unfi 6798 asks, could some of those moving stars be asteroids like the ones currently detected? It's quite close to the Earth's orbit.
Yes, in fact, a lot of the moving objects that we see are actually solar system objects. I mean, a lot of the things we see when we find new alerts on the sky, find new things, a lot of them are moving objects. In fact, about 50%, maybe 40% of the objects that time domain surveys, the ones that are looking for things that are changing, are in fact solar system objects. And so this is how we find solar system objects. This is how we follow them up. So that's a very important part of time domain astronomy, is being able to detect and identify moving objects. And the ones that are closer to the Earth in general are moving faster. And so they often appear as streaks. And so you definitely want to be able to find all of those, because we would really, really like to know where all the ones that are close to the Earth are. That's a very important task that many astronomers are working on.
Absolutely. And I think we actually just had a press release come out yesterday on a near Earth Trojan. I think one of the nearest ones. Rob, am I right about that?
The second Earth Trojan found, which is the largest of the two that have been found. So
yes.
So yes, you have. That's on our website at noirlab.edu.
Excellent. I will drop that link in the chat. Thank you so much for that question, and awesome response, Tom. Thank you.
And I've got another comment and a question from the Facebook chat, Tom. First of all, Eddie says thank you, and he's now your biggest fan.
Oh, well, I need as many fans as I can get.
And then we have a question from Gina Marie. This is a technical one. We'll see if you know about this one. I've heard of this object, but I don't know as much about it. The binary star system KIC 9832227 was predicted to have a stellar explosion, a red nova that would take place between 2018 and 2020. The estimated time frame has changed to 2022, and she wants to know about this new time frame still accurate. If you know anything about that particular object.
I don't know details about that object, so I'm not sure why they changed the time frame, but I can guess that often in astronomy, the initial information you derive is from what little information you have, and you try to learn as much from that, and you extrapolate from that. And sometimes that doesn't necessarily give you as precise an answer as you might hope. And as you learn more, that's when you refine your predictions. And so I imagine that's what happened here, is that as they watched this object more carefully, they got to understand exactly what was going on better, and the models would give them a much better estimate of how things would happen. This is true of every major change in astronomy, is that you really want to make sure that as you get more information, you get a better picture of what you're looking at. If you're not getting a better picture, that's often a sign that you're wrong.
And a follow-up just came in. Gina Marie just posted a follow-up. If and when this happens as predicted, will the burst be bright enough to see it from Earth? And will it be part of the Cygnus? I think it is in Cygnus, but I don't know if it will be bright enough to see from Earth. I mean, bright enough without a telescope, I assume.
That's another question where I don't know the answer to that. It depends on a lot of factors of whether that would be visible to the naked eye. Those kind of novae are kind of variable, depends on the gas and dust between us and it, whether it would actually be bright enough to see. So I'm sorry, I don't know the answer to that question.
Okay. Thank you, Tom.
Mhm.
And I have one more follow-up, Tom. In your response about the near-Earth objects, you mentioned time-domain astronomy. Could you give us just a brief explanation of what time-domain astronomy is?
Well, so time-domain astronomy is essentially just the study of anything that is moving or changing in the sky. And like I said earlier, that basically encompasses everything because everything is moving or changing at some level. Specifically, though, it's when you are studying the aspect of things that change. And so there are specific surveys that are taking pictures of the sky on a regular basis. And so that's how we often find these things that change, is by looking in a consistent and systematic way. And that's what I think most people would think of as that's time domain astronomy.
Excellent. Thank you so much, Tom.
Okay, thanks. So the blink comparator was a useful thing, and it enabled you to find a lot of interesting things. But the real big change in astronomy came with one of these. This is a charged coupled device, a CCD. And this is a great thing to use for taking images. It's much better than a photographic plate because this can record 99% of the light that falls on it. So it's 100 times better than a photographic plate. Now, when we first started using these in astronomy, they were expensive and small, as you can see from this picture. So it was hard to do images of large areas of the sky. And so it was not as effective a tool for some of the time domain things that we would talk about. But of course, they've become much cheaper. I'm sure everyone listening to me has one of these sitting in their pocket in their phone. This is how everyone takes pictures nowadays. And so there's really been a revolution in how imaging is done, not just in astronomy, but for everyone. All of us have really gained from the technology that's produced these things, but they have been really effective in astronomy. So how do we find things when we use one of these? Well, if we're lucky, there's an arrow pointing to the object and that tells us where it is. But the actual best way to do it is to use the fact that when you take an image with the CCD, like on your iPhone, it's a digital image. And you can take another image, and that's also a digital image. That means you can take them in the computer and subtract them. So this shows epoch 1. That just means that's an image taken at one time. Epoch 2, that's an image taken at a different time. And if I take those two images, put them in the computer and say, subtract them, well, everything that is constant gets subtracted out because they're the same in both image. And the thing that has changed is now obviously visible. So no more blink comparator. Now we can do it in a computer. And the best part is the computer can find everything that's changed. We no longer need a person to look at all this. We can automatically find everything that's changed. And the other thing is that it's incredibly powerful. You find subtle things. So here's another image of the Large Magellanic Cloud, that satellite galaxy I mentioned earlier. And if you look at that, you see the gas and dust that make up that galaxy. But if I come back a year later and take a picture of this and subtract the two, I see this. Now that's something you didn't see in the other image. And if I come back a year later and take another and then subtract that as well, they move. And another year, and they move again. And I'll cycle back through that. And you'll see that over time, those rings are moving out. Now, the center of that ring turns out to be that supernova that I showed you earlier. And these things that are moving out in rings away from that supernovae are in fact light echoes. These are reflections of the light from that star that exploded. And that light goes off and bounces off something and comes to us. And it takes a little longer to get to us, so we see it after the fact. And it is reflecting off different things throughout that galaxy. And so that's why you get different circles as you get further away from the supernova itself. So here's something really spectacular and subtle that I don't think if you were using a blink comparator, you would have noticed. Only because of this digital image subtraction, it's provided us with this incredibly powerful tool to find even the least significant changes like this, very subtle things. And it's just a spectacular result. So now we can do this image subtraction. We can really find things. And this is where the technology starts to drive things in ways that are making things explode, literally, in terms of how we are doing things. One is we can make really big telescopes now. So on the left, you see the Keck telescope, and on the right, you see the Gemini North telescope. And the Gemini North telescope looks bent. It's so big, they had to use a wide-angle lens to take the picture. That's how big it is. So we can make big telescopes, but we can also now make big cameras, and that really helps. So this is the dark energy camera. Okay, so on the right, you see an image of the camera itself, and each one of those little rectangles in there is, in fact, one of those CCDs. It's pretty big. On the left, you see an image taken of the sky on that. Now, most people nowadays, if you've got your digital SLR, you're proud of like tens of megapixels. This is a 520 megapixel camera. Now, if you look up above that image of the sky, in that red circle, there's a little square. That's what an iPhone camera is able to do, compared to what this DECam imager is able to do in a single shot. Now, this is deployed on one of our telescopes down in Chile on Cerro Tololo in the Blanco 4-meter telescope. If you could see in this tiny little image of me on your screen, it's the one over my right shoulder here. So that's where that camera is right now. And it's one of the things we're using to try to look for changing things in the sky. I see Jamika has another question for me.
Hi, Tom. That is such a useful comparison. What our CCD camera and our smartphones can see versus DECam. Huge difference. Okay, so first, let me share a comment from Airborne Verbs podcast. Michael Mosby says, "Thanks so much for having such a great presenter and presentation. Loving the questions and responses." So, all right, Robin, Tom, thank you, thank you. Okay, now we have a question from Eric Gregory. Eric asks, when the LSST begins collecting data, how frequently will the data be reviewed to find changes, considering how much data will stream off nightly? Will we start seeing changes from night to night?
Yes, we will. And in fact, that's what I'm going to get to in a couple of slides. So if you stay tuned, you'll get the answer to that question.
Fantastic. Well, then I will just wait for that one, and I'll share this one more comment from Unfi6798, who says that they also use CCD cameras when hooking up with SETI on checking out the skies, and they say it is quite accurate, Tom.
Okay, thanks. So yes, the big cameras. So this is the technology driver that's really it, is that we can actually build these enormous cameras that are just fantastic at taking images of the sky. And so the cameras have really changed how we look at things. And so on the far left, you see the Kate telescope. So way back in the dark ages, when I was in grad school, my advisor built this telescope to find supernovae, but it has a tiny little field of view, 45 square arc minutes. An arc minute is a 60th of a degree. And just for a scale, the full moon is about a half a degree by half a degree. So that thing could maybe picture the whole moon. And so we were lucky to find dozens of supernovae in a year. Right now at Mount Palomar, Caltech is running a survey called the Zwicky Transient Facility, and they have an enormous camera on there. It's 47 square degrees, but it's a small telescope, so it doesn't see things that are too faint. But they still find dozens of these supernovae a week now, because they are able to do much more of the sky on a consistent basis. And then the Rubin Observatory's LSST, that's the camera that's going to go there. It's an enormous field of view, 10 square degrees, and it's on a big telescope, so it sees faint things too. So there we're going to find dozens of supernovae a night. So you can see there's dramatic growth in what we're able to do, because we're able to make bigger and bigger cameras and put them on bigger and bigger telescopes. And so here's a movie just to illustrate how big that change has been. These are all the supernovae. So this is just one kind of transient or variable object in the sky, just one. And you may have noticed at the beginning of this, there were just a few. That's because the first 500 years is a second. And then after that, we start to find things in an automatic way. And when you see patterns on the sky, that's not where the supernovae are. That's where the survey looked, because telescopes weren't able to cover the whole sky at once. They could only look in certain places. But you can see that there's just this tremendous number of supernovae going off all the time. And it's so many. How do we actually follow all these? How do we search it? How do we look at these in detail and understand them? How do we use these to learn more about supernovae? There's just so many of them. How are we going to keep track of all this stuff? And like I said, it's one kind of object. There are dozens and dozens of kind of objects where you could make a similar visualization that shows all of them going off across the sky all the time. So it's a tremendous problem how you sort through all this stuff. But it's been a dramatic growth in that. So we're here back to the beginning. You see that's the first 800 years right there is those three. But as we heard, the big thing coming is the Vera Rubin Observatory. This is a telescope that NOIRLab is constructing in Chile on Cerro Pachón. You can see it from across the hill from the telescope over my shoulder where our other facilities are. And it's named after Vera Rubin, who was one of the great astrophysicists of not just of the United States, of the world. She was an amazing person, and she demonstrated the existence of dark matter. She was a key person in doing that. She was just a fantastic astronomer and a wonderful person. So it's an honor that this building is named after her, and I'm really proud of that fact. Inside there will be this enormous camera that you can see, but there's also this enormous telescope. And just to give you an idea, that telescope really is big. Those are people all around it. That's how big that thing is. And so this stuff is all being assembled right now and put together in Chile, and will turn into this Vera Rubin telescope that will conduct this legacy survey of space and time, or LSST. And here's a little movie showing how it intends to take images across the sky every night. And so what it'll do is, with that big camera it's got, it'll take an image and it'll move to the next spot and take an image and so on. And over the course of a night, it can do about 1,000 images. And it's going to do this every night for 10 years. Now, 1,000 images covers about a quarter of the visible sky. They actually repeat a lot of images because that's how you find solar system objects. So it's more like an eighth of the sky. But essentially everything visible to it, that is the southern sky that's visible from Chile, will be imaged at least once every 3 days. That's how often we'll come back to see the same spot with LSST. So if it takes those 1,000 images every night and covers the sky every 3 days, we think that each of those 1,000 images will produce 10,000 new things. So there will be 10,000 things that have changed in brightness or position in every one of those 1,000 images. That means that there are 10 million things that have changed in brightness or position every night for 10 years. And we have to figure out how we're going to deal with that enormous volume of data. And so, in fact, people often liken this to a fire hose. But I think this totally underestimates it. I think it will feel like this. This is what it will feel like when you've got 10 million things pouring out at you every night. And so this is another project at NOIRLab, is to try to figure out how we can do that. And so this is the project I'm running, where we're trying to build a system that looks at the alerts and then uses everything we know about the light coming from that object and other observations of it to try to sort out what things are. And so we're running right now on that survey from Mount Palomar. Well, we're running, except their camera has been broken for 6 weeks, so we aren't running right now. But if we were, you'd be able to go and see things happening live. You could go and look at new data right now. And even though this is intended for professional astronomers, I think anybody could go to this website and start poking around and looking at these things and just see the great variety of things that are out there, how they change, how they change and what they do when they're changing. It's a really interesting thing to sort of page through the various things that we're able to process. And if you have an idea about how to find something, you can write a filter if you know Python, and we'll run it and find the objects you're interested in right now. But I don't want to talk any more in detail about that. If you're interested, you should just go to that website and start playing around. So, Jamika, do you have another question?
I do, Tom. This is fantastic. I will definitely make sure that we have the link to the Antares page in the video description once the final edited recording is posted. So question for me first, Tom, on average, how many supernovae do we expect to find per galaxy every 100 years? Are there very many, or is it a small amount?
It's usually like 1 or 2 in 100 years in a typical galaxy of our size. So that's not frequent when you're looking at a galaxy, but if you're looking at billions of galaxies, that starts to add up. And as it turns out, there's probably a supernova going off every second in the observable universe. So That's just because there are a lot of galaxies out there.
Yes,
But of course, we're
brilliant.
overdue for one in our own galaxy. The last one that was visible in our own galaxy was the one that Kepler saw in 1604. There may have been ones on the other side of the galaxy that we didn't see, but it has been a while since there's been one in our own galaxy.
Is Betelgeuse one of in the top left of Orion's shoulder, the constellation of Orion? Is that one of the stars in our galaxy that we expect soon-ish to go supernova?
Yeah, it's probably one of the most likely ones to go. It could blow up right now, or it could be several 100,000 years from now. It's hard to know for sure. It did undergo a very interesting dimming a year or two ago, and people thought that might have been a prelude to some kind of really significant change. But as it turns out, it was just dust moving in front of it. So it turned out not to be as exciting as you might hope. But on the other hand, that's the way things go. But when it does blow up, it'll be spectacular.
It will be spectacular. Oh, wow. Okay, so we have a question here again from the chat. From the Memphis Stargazers, Liz Fleming asks, what is your most intriguing discovery so far, Tom, and why?
Well, I think there are a couple of things I choose, but I guess one of them is a little esoteric, and that is when I was in grad school, we found a supernova, and I looked at it, and there were unusual things in the spectrum. The spectrum is where we take the light and spread it out into its colors. And by doing that, you can see the elements that the object is made of. And this was an unusual thing. And it showed helium in ways that were not usually seen in supernovae. And in fact, we discovered what I think was the interaction of the supernova. The supernova was blasting into stuff that had this helium in it. And as it turns out, nowadays, that's a whole new class of supernovae. I didn't recognize what I saw because it was just so weird. I didn't know that was a new thing. But now there are many of them. And so it turned out I saw the first one. So that's probably the most unusual thing that I've done.
Oh, wow. That's pretty amazing, Tom. Wow. Yes. Okay. And then, Tom, we have another comment and question from Unify 6798 in reference to the Antares Project. The comment is, I'd like to be involved with that project. What is the procedure? Can they find that information on the website, Tom?
Yeah, if you go to the website, there's a fact page there about what you can do with the system and who to talk to about how it works. And so, yeah, if you're interested in this, we're happy to talk to people who want to look at it. Now, like I said, it's designed for professional astronomers, but I think anybody could really could find something interesting to look at.
That's amazing, Tom, that regular everyday people can interact with this kind of software program that allows you all to be able to process all of these alerts. And I know that this is certainly heralding in the era of big data. Is this big data, Tom?
This is big data. We anticipate that by the end of the LSST survey, that just our database of the alerts, which isn't images, right? This is just information, will be like a petabyte scale database. So that's enormous.
Wow, that's actually hard to fathom. Hard to fathom. Wow. Okay, I will make sure that Unfi 6798, that link will be in the video description as well. We'd definitely love for you to interact with Antares. Thank you, Tom.
All right. So at the beginning, I said I'd show you some of the interesting science we can do with time domain, because we've talked about the history and the technology, but what are we actually doing now? And so I want to show you a couple of things that I think are kind of interesting that I've worked on in some small way. First, I'll show you a little bit more about light echoes. But before we get to the light echoes, I want to talk about multi-messenger astronomy. And this is a really interesting thing that is new about how astronomy is done. And that is, from the beginning of the human race until a few years ago, everything we knew about things in the sky was from the light that was either emitted from them or was reflected off them. That was all we could do, was look at things and record that information. And light might be optical light or infrared or radio or X-ray or something like that, but that's all we had. Now we went to the moon and brought rocks back, and we've been up to the upper part of our atmosphere and brought back interstellar dust particles, and we've sent missions to bring things back from comets and things like that. But virtually everything beyond our solar system, we only know what it is because of the light that comes to us. But that's slowly starting to change as we're able to detect other things that are emitted or produced by these astronomical sources. And so that's why it's called multi-messenger, because it's not just light anymore. There are other things we can use to study and understand objects in the universe. So one is cosmic rays, and we've known about these for a long time. These are high energy particles that come from astronomical sources and crash through our atmosphere and interact with things here on Earth. Because they change path as they move through our galaxy, because they're charged particles and there are magnetic fields, it's hard to trace them back to the origin. So they're useful, but it's hard to say exactly where they came from. So it makes them harder to use to study individual objects. Another thing we can use are neutrinos. I mentioned this earlier. These are subatomic particles that are generated in some astronomical sources. And they don't interact with much. There are trillions of them flowing through your body right now from the sun, and you'd never even notice. But we have built detectors that can capture these. You need enormous machines full of material that can interact, and even then you might see a handful. But we can see them from the sun. We did see them from that one supernova, indicating a neutron star was formed. So that's really exciting. Now we can actually see something, and we know where it comes from by using these machines to try to detect them. And the one that's really interesting right now is gravitational waves. And this is a consequence of Einstein's theory of gravitation, that when masses move in space-time or accelerate in space-time, they cause ripples in space that can propagate out. And we can detect these things here on Earth by using special observatories. So here's an animation showing how if two masses are moving around each other, they will cause ripples, and those ripples will propagate out away from it at, we think, the speed of light. So this doesn't exactly show how fast they're coming, but those ripples will move out and eventually come to us if one of those things happens near enough to produce a wave that is big enough for us to detect. And so we built these detectors that are essentially long arms that look for changes in the distance between the building in the center and the end point of those arms. And those changes are caused by the wave in space distorting that distance. And in fact, we've actually done this. We've detected gravitational waves. But the gravitational waves, these observatories aren't very good at pinpointing on the sky where the event happened. And so it can actually, any individual one of these observatories, it might be, well, it happened in that half of the sky or in this quarter of the sky. So it's an enormous region, so it's hard to pinpoint where it happened. But if you have more than one, you can try to triangulate where that object is. And so on the right-hand side, you'll see an event from a few years ago where 3 different gravitational wave observatories showed where it's more likely to find the object because they all overlapped in a much smaller place than their entire area. And so by looking in that one particular place and looking where the galaxies are, in fact, you found something new. And so on the right, you see, by looking in that one particular spot on the sky, there was a galaxy and there was a new object that was near it. And it's what we call a kilonova. And that is 2 neutron stars that merged. And this was something that was predicted but not seen before. It took that gravitational wave observation to point us in the right direction to find that new object. And so this was really spectacular. It confirmed Einstein was right because, as it turns out, he was always right. But now we really are seeing the universe with different eyes. It's changed how we think about massive stars. It's really amazing that we're able to do this now, that we can see these things happening, that we can find these waves in space and find these massive objects coalescing into each other. Now, the light echoes. This is another thing that I find really interesting. So here you see the supernova at one end of this ellipse and the Earth at the other. And the light, when it blows up, comes straight to us. But it can also go bounce off these dust clouds around it and eventually come to us. And you'll notice that, like any triangle, the fact that the light has to go off to the echo and then to us, that's a longer path. And that means the light takes longer to get to us. So we see the echo after the supernova happens. So if we look around where that supernova that Tycho Brahe saw in 1572, we can find little patches of light, and they're moving just like a light echo. And if you follow those lines back, those blue lines indicating the motion of those light echoes, they point back to where Tycho saw that supernova. So we can see the same supernova that Tycho saw. We can rerun what he saw in 1572. We can look at it now. And even more interesting, just like when you go get your haircut and the barber or the cosmetologist holds a mirror up behind you so you can see the back of your head, if you're looking at this reflection of light, you can see the object from a different angle, something we've never been able to do. Outside of our solar system, every object we've ever looked at, we've only seen the side that's pointed at us. But now we can look at it from every direction. And in fact, in this case, it showed that the supernova looked different from different directions, telling us something about how it explodes, that it's not a simple sphere expanding, that something really different is happening there. So it's amazing that we can actually use these things to peer at an object from different angles. Another light echo we can find is from this star. This is Eta Carina. And Eta Carina is a star that varies all the time. And we've known this for a long time. If you look at that top light curve, it's 400 years of observations. But we can find light echoes of that object cruising along. And then we can go and look at those light echoes and we can replay the event. We can rerun that explosion from the 19th century over and over and over by looking at different places. So it allows us to go back and pretend like we were there in the 1840s. But now we can look at it with modern instruments and we can use this to understand even better what was going on with the star. So I think this is just a really amazing thing that we're able to do this with these light echoes. And it's one of the things you can only do with time domain, because it's only by watching these echoes move along that you're able to figure out what they are in the first place. So it's been really fun to work on them. But I just want to leave you with one point, and that is those telescopes are good, like LSST, are going to find millions of objects. And if we don't look at them and understand them, they go away. Because here's the drawing that Galileo made in December of 1612, showing the Jupiter, its moons, and off to the side, he drew a star, saying, "No, I see the star over here." But if you wind the solar system back to that point, and you would find that that's not any star, that's Neptune. So Galileo saw Neptune, but he didn't recognize it for what it was. I mean, how could he? But he saw it 234 years before it was discovered. And so we don't want that to happen with LSST. We don't want to detect things, but not figure out what they are, because they could be something really amazing, like finding another planet. So that's one of the things that really motivates us now is, how do we do this? How do we keep track of the fact that we can harvest everything in the sky, but how do we sort out what's what? So that's the big problem right now in time domain astronomy, is making sure that we don't miss anything obvious like that. So I hope I've been able to convince you that everything in the sky is changing, and how that changing stuff has really changed our view. And that by looking with very carefully, that helps us to understand what the objects are, but that the technology has driven it. Now, big telescopes and big cameras have really made it so that we find everything, and that's made it harder. But it has opened up whole new worlds for us, and we're going to keep doing that. We're going to keep exploring and keep looking at these to see what we can understand about the universe.
Wow, thank you very much, Tom. That was fantastic. So, I don't see any more questions in the Facebook chat. Jamika, do you have any more questions or comments from the YouTube audience?
I currently don't. I think that's all the questions and comments that we have from the YouTube audience. I would like to share that we had people from a wide range of places, including Christmas Island, Memphis Stargazers from Memphis, Tennessee. We also had people from the Bay Area as well. Oh, and now that I just said that, we have one more question that just popped up, Tom. A question from the Memphis Stargazers. Liz Flemings asks, are your images available for future references? Can they be obtained?
Yeah, so all the images that we take now are archived. So we do keep everything. Sometimes those images, depending on who's taken them, they might be proprietary for some period of time. But usually within a year or so, All that data is public. So if you want to look at any of these, they're all available. And certainly things when they change, the information that comes out as alerts, that is public. So the things that you see on the Antares website, that's real-time information. Anybody can have access to that. We don't have any restrictions on anybody using it. That's the philosophy of NOIRLab, is make everything available to the people who can use it.
That is a brilliant philosophy. I'm so glad. I assumed that they were available, but I am glad that you confirmed that.
Mhm.
Thank you, Tom. And thank you to everyone who joined us in the YouTube audience today for your comments and questions. We really appreciate your participation. All right, Rob.
Okay, thank you again, Tom. That was a wonderful presentation here. We're just about out. We're running a couple minutes over, but before we do go, Jamika, do you have a preview for next week's Live from NOIRLab at Gemini, or next month's, excuse me?
Yes. I am pleased to be hosting Live from NOIRLab at Hawaii next month. That's going to be the first Wednesday of March 2nd. It'll be at 2 p.m. HST, 5 p.m. MST. And our guest will be Kim Venn, who is a professor of astronomy and physics at the University of Victoria in Canada. She'll be speaking on our newest stellar stream press release, C19. And if you're not familiar with what a stellar stream is, a stellar stream, and I will make sure that we have the link in the video description. The stellar streams are collections of stars that once actually resided in globular clusters. These are groups of very old stars that are very tightly bound together by gravity. But they used to provide. They used to be in these globular clusters and these dwarf galaxies, but they've been actually torn apart by gravitational interactions, and they've been distorted into these long waves. One thing that's really interesting is that these are low metallicity stars formed early on in the universe, and so that gives us insights on star formation and galaxy formation early on. Some new insights. So I'm very much looking forward to having Kim Venn with us on the 2nd of March, and I hope you can all join us as well.
Okay, thank you, Jamika, and thank you once again, Tom.
No, thanks again. This was fun to do.
This was a lot of fun on our end too. So, and I'll be signing off, and we hope you can join us in the March edition of Live from NOIRLab at Hawaii. Bye, everyone.